Hi. The reversible method of enzyme immobilization relies on the non-covalent interaction between the enzyme and the solid support. These methods, in these methods, we can actually recover the enzyme after immobilization if you want. That's advantage, and disadvantage is like the attachment of enzyme with the solid support is not stable. So due to the repeated use, it may leak out. It's a problem with the non-covalent interactions. First method is adsorption. The enzymes are adsorbed due to the non-covalent interaction to the solid support. It's a simple and easy to do method. It do not significantly alter the cold catalytic activity. If we are doing the covalent binding or the cross-linking, it will actually affect the enzyme activity because we are modifying the covalent bonds of an enzyme. But in this case, it is not affected. Disadvantage is like enzyme is leaked from the matrix because it is a non-covalent interaction. By using different types of bond formation, we can actually achieve adsorption. Non-specific adsorption is there. Ionic binding, especially if the enzyme has a particular charge, we can actually immobilize into a matrix with a different charge. Hydrophobic adsorption, which is very strong in nature. Affinity binding. Affinity binding, we make either antibodies or cofactors, which is immobilized in the matrix. So as the antibody is immobilized, the enzyme bound to the antibody will be also immobilized. So such way also we can actually immobilize the enzyme. The problem with ionic bonding is like ionic bonding is always in dynamic equilibrium. So even if the enzyme is bound to the medium, bound to the support because of the opposite charge, it is all easily reversible. And if a change in pH or ion strength happens, the enzyme will be detached from the surface and it will be leaked. But it can actually easily recover the support. And another problem is like if our substrate or product is charged, it will also go and bind to the solid support. So ionic bonding is not that much recommended for many enzymes because of these limitations. Polyethylamine coated support used for the immobilization invertase, urease and glucose oxidase. It is used, but the downside is that it is easily reversible. Like anytime enzyme can be leaked into the medium, and our substrate and product should not be charged. If it is charged, it will go and attach to the solid support. Hydrophobic interactions are very stable under high ion strength conditions. It's an entropically driven interaction. In the affinity binding, it's biospecific interactions. We can either use an antibodies against the enzyme or cofactor analog of an enzyme to immobilize the real enzyme. And sometimes we use the isolation of the enzyme and immobilization simultaneously. We will actually study those processes in next semester. In brief, what we do is like we will do a genetic engineering. By this process, what we do is like we will attach some biotin components into the enzyme. By genetic engineering, the biotin will be attached to the enzyme, and after production of this enzyme, we will take the microorganism and break it open, and this mixture will be added to a solid matrix, and the solid matrix will contain streptavidin, and streptavidin has a very high affinity to the biotin. If our enzyme is having biotin and you are adding into the column with the streptavidin, they will go and bind because of the affinity interaction. This affinity interaction is very strong in nature. In that way, we can actually isolate the enzyme, purify the enzyme along with the immobilization. Those columns can be used for the enzymatic process. That's what we call the simultaneous isolation and immobilization. This adsorption can be also used for the immobilization of the whole cell instead of the enzyme. Okay, the whole cell can be immobilized using adsorption. Metal binding, which is also a reversible method. Actually, the metals are the charged metals are used for immobilization. So in this case, like solid support like cellulose and chitin will have metal salt precipitated into the support, and this metal salt will be aiding the binding of enzyme to the solid matrix. Most commonly used metal salts are titanium and zirconium. Then it's a simple method. A high specificity activity of enzyme can be supported because there is no covalent bond between the enzyme and the product. but the downside is like low operational stability and non-uniform absorption. The different places it will may absorb different amounts of enzyme, which leads to the non-uniformity, uh, which can be avoided by actually first do an absorption of like chelators, metal chelators into the solid support, and to this metal chelators we can add the metal compounds. So this metal compound will be bound to the enzyme. So first we have the solid support. In the solid support we will immobilize the metal chelators. Metal chelators have a strong affinity for metals, so it will go and bind to the metals, and this metal will be binding to the enzyme. So in that way we can actually make it uniform and more stable. And the attached enzymes can be easily diluted by changing pH. If you want your enzyme back in active stage, just change the pH or add a soluble ligand to it. Okay, EDTA can be used as a chelator for this process.